comprised of Matthew Young, Jack Zarbach, and Connor Hopkin. We are doing a temperature control experiment with a cooling fan, and this is to simulate a cooling fan for a computer that would cool it down so it doesn't overheat and runs right.
So here you can see a block diagram of our system. Here, a set point is passed in, and an error is calculated from the difference between our set point temperature and the temperature reading from our temperature sensor. This error is passed into a PID controller right here, which outputs a fan speed, which in turn affects the temperature. There's also a disturbance from heater value here that also affects temperature. However, we're going to correct for that using a feed-forward element that will also be accounted for in our PID controller. Now over here is a picture of our actual system. Here you can see we are using two Arduinos. One of the Arduinos is connected to this fan using this breadboard, and it's being used to cool our TC lab right here. And here's where the temperature sensor and the heater are.
For our physics-based model, we used an energy balance to find the change in temperature per time. As you can see here, we've got convective cooling, got radiative cooling, and of course our heater input. And our convection coefficient is a function of fan speed. So as you can see in this graph, we performed multiple step tests at different fan speeds with constant heater inputs. And then using regression found h for each of those fan speeds and created a function of v for h, and then passed that in to our simulation.
And now here we have our feed-forward element being calculated. So this is our PID equation with our K feed-forward here at the end. Since our disturbance is our heater, we did a step test on our heater and found a gain of 0.6. Using this along with our gain of our fan, our Kp, we calculate our KFF, which accounts for this disturbance and would improve our controller.
So here you can see the fits for both our physics-based model and our FOPDT model. So using our physics-based model and the function generated for the convection coefficient, we were able to simulate our step test data pretty well, as you can see here. And then on the right over here, we regressed our FOPDT equation to fit a different step test right here. And we did this to calculate optimized values for Kp, Tau p, and Theta p, which are used to calculate PID parameters.
To get to our PID parameters, from our FOPDT parameters, we used aggressive IMC tuning correlations. And the aggressive correlations were used because overshoot was not a problem for our system. We're trying to decrease the temperature of the heater to a certain set point, and going slightly colder isn't an issue. And on the right, you can see our calculations to get from the FOPDT to the PID parameters.
So here you can see our final PID controller. As you can see here, these values are the same as these values because our original tuning parameters actually gave us really good PID parameters for this fit. However, we found out that using a feed-forward element saturated our controller and didn't give us a very good fit. And using a tau d value would actually cause our fan speed to fluctuate too quickly and also throw off our fit. So we actually got a really good fit just using a PI controller. As you can see right here with an IAE of 1770 basically, we were pretty good at controlling this temperature even with multiple set point changes and sizable heater disturbance value. Now here, you can see here that it doesn't actually reach this temperature set point. That's because we're trying to get a set point of 30 degrees, and our ambient temperature is pretty low, is pretty close to this 30 degrees. So that cooling power that convection provides is pretty small at this point because that temperature difference is so small.
As for stability, we use the shortcut method for our overall transfer function, which includes our controller transfer function and our fan speed transfer function. Here for the fan speed, we assumed a first order model, Kp over tau ps plus 1. And for the controller transfer function, we used the one we derived in class. Plugging those into our G of S transfer function, we got a big fraction, but we only need the denominator for the Routh array. Using the coefficients, we calculate an minus 1, an minus 2, and so forth. But we only really need this left-hand column to be positive by varying Kc. Giving these Kp, tau I, and tau p values in an minus 1, for this to be positive, Kc would have to be less than 9.05. However, in B, seeing that Kp is a negative number, the only way B could be positive is if Kc is also a negative number. So with this being the more restricting requirement, we went with a Kc less than or equal to 0 for a stable controller. And as you can see, our controller used a negative Kc value, which produced a great controller to control the temperature of the TC lab.